All right, hey everyone. Thank you for joining our webinar presentation here today. We'll be taking a look at the accelerated thermal conductivity testing for geological applications. My name is Ari Heikkinen. I am an application scientist here at C-Therm Technologies. I'll be basically walking us through a little bit of an introduction, a little bit of info on C-Therm, and then diving into some application content. Taking a look at some various methods for measuring thermal conductivity specific to geological materials. So with that being said, we'll go ahead and jump right into it. So a little bit of background on C-Therm for those of you who may be new to our webinars or haven't previously been on one of these with us. C-Therm, essentially, our goal is really to simplify thermal conductivity testing for the materials of tomorrow. We do this through the advancement of various transient-based measurements for thermal conductivity. Here we kind of see an image of our flagship product. This is called Trident. Trident was developed and launched, I believe it was the end of 2019, so a few years ago now. It is unique in the sense that it is a modular platform. So you can see there's 3 different sensors there connected. So the transient plane source, the yellow flexible sensor on the left, the transient line source, which is the needle probe in the middle, and then C-Therm's proprietary method, the MTPS or Modified Transient Plane Source, you can see on the right. Throughout the session here today, we will be focusing in on applications and uses of all 3 of these methods. Really, I would say in the space of geology, there's quite a range of sample types, and as we'll kind of get into in the session here today, we'll see that there will be cases where one or maybe multiple of these sensors may be applicable to that specific sample type. So I'll be going into further detail on this as we get going there. I will just make a note, you may have seen a few of these comments dropped into the chat box already. So on the right of your screen, there should be, there's a chat box function. If you have any questions, feel free to drop those in. My colleague Engad is moderating our session here today. He'll be posting various links to some of the things I'll be discussing, as well as trying to assist with any questions that do pop up. At the end of our session here today, we will go through a little bit of a Q&A. So if you do have questions, just feel free to put those into the chat box. Now with thermal conductivity, there's, even within the Trident platform, having 3 different methods, really understanding which method is best for your given application, the sample, the test conditions, things like this. It can be confusing, especially if you're new to this topic. So we do have this available as a free download on our website. It's a method selection guide. It encompasses the transient methods that are available on Trident, as well as other methods, more traditional steady state techniques, other options such as laser flash. We kind of discuss, the benefits of each of them and, where the limitations lie. So definitely, if you are new to this space or just simply want to get a little bit more, this is available as a free resource. So feel free to take advantage of that. And before going into the bulk of our session, we always like to kind of highlight some, basically what are our clients saying about us. This was one from David Lombardi, working for the Seaforth Geosurveys. They actually have one of our MTPS sensors. They are taking in situ measurements of some of their samples. I believe it is on a kind of a test vessel that is, they're collecting samples and testing it right on the boat as they're being extracted from the seafloor, if I'm not mistaken. But again, they're using the MTPS and really mentioning they recommend this for anyone kind of doing research or screening with a focus on geological materials. So just a nice little shout out there from David Lombardi. And again, we have a range of different client testimonials on the available on our website. So if you're looking something more specific to your application, there are some folks that might be talking about how the system has been used and working for them. But with that being said, we're going to kind of now pivot into the bulk of our session here today, which is again taking a look at some application-specific content here on geological sample testing. So I'll kind of just start with, very high level, very kind of just basic background information. When we're talking about geology, like what are we referring to? So, this is an earth science which studies, various structures and compositions of the earth, so rocks that form throughout these different processes and how they're developed and changed over time. Some of the groups that we work with, they actually are in the field of analyzing different materials in kind of in space, so on different planets. Geology can be applied to this type of studies. It's sometimes referred to as exogeology. But in all cases, it's really the study of the material of the system that you're looking at. Now, again, if you're new to this field, thermal conductivity, just as a refresher, what is it? What does it really tell you? What does it mean? Essentially, thermal conductivity will describe a material's ability to conduct heat. It's an intrinsic material property, so this is independent of the shape or the size of the sample. And for all of the content that we'll be looking at here today and kind of the values and kind of results that we're looking at, they're reported in units of watts per meter Kelvin, which are the standard SI units. So, where does thermal conductivity play a role in geology and these different earth sciences? Mainly, this is where anytime you're going to have heat transfer, where heat transfer is an important aspect to some type of process. So kind of a few points there, different things looking at mantle convection, volcanism, geyser eruptions, hydrocarbon deposits, understanding and really being able to quantify that heat transfer is going to be good to get a better knowledge of how these processes are occurring. And in situations where you are going to perhaps go for a extraction within the ground, looking at different evaluations for geothermal applications, understanding the thermal conductivity of the matrix that you're working in is really going to be important to make sure that, one, it's safe to do so, but then also making sure you're doing so in an optimized manner. So when we talk about geological samples, there's quite a wide range. Certain groups that we've supported and worked with in the past, these can vary from things like, core drillings of different kinds of rock formation, sediments, application of testing soils, rocks, aggregates, and also I included the oil and gas area here because this is, I'd say, a specific offshoot of geology, I believe generally referred to as petroleum geology, where you're primarily looking to extract some of these resources from the ground. But again, understanding how the thermal behavior of the sample and also the surrounding area will play an important role in these different applications. On top of the different sample types, there's also some specific test conditions or environmental conditions that can really play a role in how the heat is transferred within the material. So whether you're looking at something at room temperature, subambient or elevated temperature, this can have a significant impact on the performance criteria of these different materials. Understanding aspects of things like pressure, so whether that's a mechanical pressure or under a specific gas environmental pressure, this can also play a role. And another one here to take a look at, which we'll highlight in a few examples as we go through, is also saturation. So whether it is a dry material or if it's saturated, semi-saturated with some kind of fluid, again, these different aspects can play a role in the overall thermal performance. So when you're setting up your test conditions, really having these controlled for and adjusting for them will really be important to getting that really good quality, accurate data. So I won't go into a big background on the different thermal conductivity test methods, but as I kind of mentioned previously before we got started, there are a range of different options. So steady state methods are your more traditional things like heat flow meters, guarded hot plate. I know the cut bar method is often referenced in some of these different studies as well, the geological space. But where we'll be focusing in on are really the transient methods. So you can see These are things such as laser flash, transient plane source, modified transient plane source, and the transient line source. And those last three are really the ones that are available on the Trident, and the three that we'll be focusing on exclusively here today. Now, again, where I mentioned the Trident platform itself is a system that is modular. It can have all three of these methods. And really, as we go through this session here today, one of the main takeaways I hope to illustrate is that especially in this space, really having more of a toolbox approach, having a multiple methods available to you is going to give you the greatest chance of success at getting good quality and representative data of your materials. And basically for the format here, I'm going to be going method by method and giving some information on the sensor itself, some of the criteria that need to be met to use the method on the samples, but then also go into some example highlights, some case examples and collected data, just giving you an idea of how these sensors can be set up and used. But why do we focus on transient-based methods here? Typically, a very high level, there's three main points that we like to kind of highlight. One, they really lend themselves quite well to representative testing conditions. So all the sensors, some more than others, they do provide you with an ability to test under different conditions. So I mentioned earlier, things like the temperature, the pressure, saturation. These types of things can affect your results, and having a test method that can lend itself to being present in those different environments can really be quite useful. The second note here is they are faster than traditional steady state options. In all cases, a transient technique will always be faster than a steady state. It's simply related to how the measurement works at a very fundamental level. But inherently, many of these transient techniques can provide you measurements within seconds, compared to, in some cases, many hours that may be required for some steady state options. And then lastly, they offer a greater flexibility on sample size. So some of our methods can test both solids, liquids, powders, pastes. Again, especially within the geological space, having access to methods that can really pivot from a solid to a liquid, vice versa, can be quite helpful, testing an unconsolidated versus a solid as well. Just again, really providing you with the ability to test something that is truly representative of your sample. So we're going to start out by looking at the Modified Transient Plane Source, or MTPS. So as I mentioned, this is C-Therm's proprietary sensor design. It is a single-sided sensor that provides some unique testing access capabilities in that kind of aspect alone. It also provides a measure of thermal effusivity. So all the methods that we'll discuss here today provide conductivity as kind of the, I'd say what most groups are interested in, but some of them will also provide a additional property. And with the MTPS, that is thermal effusivity, sometimes referred to as thermal inertia. The MTPS does conform to ASTM D7984. It is the easiest of the three methods to operate. It's also the fastest, so your standard test time with the MTPS is 1 to 3 seconds. So regardless of the sample that you're testing, it will be amongst the fastest option that we have available. And it is generally considered the most versatile. So the sensor does have the ability to test solids, liquids, powders, pastes, adaptable to high pressure and high temperature conditions. So from a principles of operation standpoint, again, just to give you kind of that high level understanding of how the sensor works. Essentially, the sensor has a spiral heating element on the top side of the sensor chip. This is what's used to deliver that pulse of thermal energy for the measurement. So as that heat pulse is being delivered, what you'll get is the system also simultaneously monitoring that change in temperature that occurs as a function of time. And really, it's within that dynamic change that's occurring over that measurement duration. That information there, the rate of change that is observed, is what's used to determine the thermal properties of the sample. With the MTPS, it's really nice in the fact that the system, it operates off preset factory calibration settings. And what that means is essentially when you set up your measurement in the software, the calibration that you choose to run your measurement will control the parameters of the test. So mainly the power level and the test duration, but then also the data, how it's analyzed and interpreted, is done automatically by the software. So you as a user are never going to have to go in and do any manual analysis or regression. It's all handled for you within the software package. One of the last things I'll just kind of mention about the MTPS here, just kind of an important note with respect to the sensor design. It's related to the guard ring. So you can kind of see that pictured in the leftmost image there. The guard ring effectively surrounds the active area of the sensor, so around that heating coil. And what it helps to do is support a one-dimensional heat transfer into your sample. It does so by preventing any lateral heat loss from occurring during the measurement. So from what the sensor is detecting over that active area, all that heat can be viewed as traveling normal from the sensor surface into your test sample. And effectively what that means for you as a user, if you're setting your sample up for a measurement, the MTPS will always provide you with a directionally dependent measurement. Here I just have a couple images of the MTPS high pressure cell. So again, just kind of mentioning some applications in kind of this space, testing under a specific environment, a specific pressure can perhaps lead to more representative data. The MTPS is one that we've had a long-standing history of integrating into these pressure cells. So again, if you were looking to gain some additional information on this, or if this was something that was needed for your specific testing, happy to continue those discussions. But these are just, one example of some of the accessories that we'd have available with the platform. So looking at our first MTPS case highlight, this is thermal conductivity measurements as a function of temperature on a crude oil sample. So I mentioned the oil and gas industry, and kind of linked to these petroleum geology applications. So extraction of these crude oils is something that we've supported many groups with. These crude oils contain a mixture of hydrocarbons. And in this example, what we're looking at is, if you take samples at different stages along the refinement process, once these hydrocarbons are extracted, they have to go through refinement and modification in order to be used and kind of, turn into gas, oil, things like this. By sampling at these different stages along the process, you can obtain some interesting information about the material through the conductivity measurement. These can be used to adjust for improvement. So the goal of what we're hoping to show in this kind of example was assess the differences in thermal conductivity between different samples. So these were sampled at different stages along a refinement process, and observe the effect of temperature under a constant pressure. So keeping pressure kind of the same here, but looking at varying temperature conditions. So we can see in kind of this table here, this graph on the right are two samples, sample 1 and 2. They exhibited two different trends. Sample 1, the one in red, noted an initial increase as a function of kind of that temperature. So going from about room temperature to 100 degrees, or a slight increase, followed by a net decrease in thermal conductivity for the remaining temperature points. Whereas sample 2, it started out higher in thermal conductivity at room temp and then showed a steady decrease over time. Now, in a very, very simple analysis here, some of these differences that we're noticing, especially at the lower level, is, as these materials are going through different temperature profiles, they may be experiencing differences related to potential contaminants, or effectively the purity of the sample as it's being sampled along the line. So by understanding how these different impurities can affect the thermal performance at these different temperatures, it can give you some information on perhaps optimizing the overall refinement process, the steps that are done along the line, where is the best point to introduce these specific refinement steps, things like this, especially if you're dealing with something as a function of temperature. And a lot of the time, temperature is a significant component to what's occurring in these systems. The next example here with the MTPS is looking at the thermal conductivity measurement of a solid that was taken under varying pressure conditions. So again, we're just looking at one sample here, kind of a sample that was tested kind of at room temperature, but under different pressure conditions. And this was all done with the MTPS high pressure cell. So again, the thermal conductivity of the solid materials can be really important to these different processes and design considerations. You can imagine the geological matrix that surrounds perhaps an area of interest will play a key role in handling thermal load and thermal stress, especially if you are doing things like extraction or again, perhaps entering into those systems and modifying them in some way. So the goal here was really to observe the influence of pressure on the thermal conductivity across a consistent temperature profile. And again, this was all done at room temp. Across the temperature profile here. So we did do some changing temperature, but on a singular sample. I apologize. So testing under ambient pressure and then also 2000 psi. So we were noting here that it's one sample, but really what we're varying is the amount of pressure. And as you can see, along the different temperature points, there is a notable difference between those two samples. So I believe one of the larger differences we saw was upwards of about 15% based on the pressure conditions. In both cases, you see a consistent trend in results. So, they are decreasing as the temperature increases, but you can see, of course, to different overall extents. And again, this really highlights the importance of testing under these representative conditions, because if you are taking this data and perhaps using it for something like a simulation input and to understand how the system will handle these different thermal loads that you're introducing, if you're assuming it to be, just ambient conditions, when in reality it's under a high pressure, the effective load that it can handle can be different. A 15-20% swing in thermal conductivity can result in a net, a significant influence on the overall process that you're working with. So again, just a potential example of where this type of representative test data becomes important. And this next example, this is still done using the MTPS, but this was a paper, it was called an Updated Ground Thermal Properties Database for GSHP applications. This was from a 2020 study, and just kind of noting here that there was many different groups involved in this. You can kind of see the different countries involved, Italy, Germany, Greece, Ireland, and Switzerland. So a lot of different contributing authors here, all working on these types of measurements. And part of the thermal conductivity data that was collected in this paper was done using the MTPS. Now, they mentioned GSHPs. So these are ground source heat pumps. Essentially, this is an application where we're taking advantage of shallow geothermal resources. So these can be used to use seasonal thermal energy. So it's energy and thermal energy that's trapped and stored within the ground, and using that in the different months. So whether it's in the winter where you need to extract heat, or in the summer where you're using it for cooling. In either case, their higher thermal conductivity in the ground area material results in better heat transfer efficiencies, and this will lead to a increased or improved performance of these GSHP systems. So that's kind of the reasoning as to why they were investigating this type of application, or this type of system for thermal conductivity. Some of the paper highlights I just kind of pulled here and summarized, but they were looking at when you're designing these new systems, you cannot disregard the local ground thermal properties. So the thermal properties are of great importance. On the little graph on the right there, these were some initial literature values that were pulled for some of these different materials, different rock samples according to the porosity and pore fluid. But one of the things that they noted here and throughout the paper was that there can be quite a wide range of thermal conductivity for these materials related to differences in such things like porosity, for example. But effectively here, what they did, they were comparing direct measurements to literature data with over 400 measurements taken on various samples. So this was a very large undertaking. where they're looking at these thermal properties. And this was a little, just a little quote I took out of the paper, but they say the most important thermal characteristics of the local underground to be taken into account when designing a new closed-loop geothermal system are thermal conductivity, and then they went into some detail, heat capacity, and also thermal diffusivity. But thermal conductivity was listed as the #1 most important property of consideration here. Now here, just kind of pulled out one of the graphs from the paper, but this was looking at the thermal conductivity results that were obtained by MTPS. The MTPS was used for a certain subsection of the materials tested. And what they're showing here is a few things. So the data that was shown with the colored bars, that was the direct MTPS measurement. The gray bar beside it would represent the literature value range noted for those samples. And then I believe the little X's that they placed across the gray bars were what they described as being, with the gray, the black crosses are showing the recommended literature values for each category. So again, there's kind of a range here, but the X's kind of hit the recommended values. And as you can see, again, even with the case with the MTPS measurements, the conductivity can be somewhat ranging, depending again on the factors of the sample that was tested. Again, perhaps with porosity being, I would say, likely one of the bigger effects here. But you can see that there is some good correlation, of course, between the MTPS results fitting in within the expected range for most cases here that were tested. But again, this is just one example of where the MTPS can come into play, some example data that can be collected with this type of measurement. And ultimately, what this information does, it allows for mapping for these optimal locations for these ground source heat pumps. The thermal data can be transferred to geothermal potential maps. These are basically heat maps that show which areas may be better suited for these types of systems. It doesn't make sense to apply these to areas where the heat transfer isn't going to really be efficient. And again, you may want to set up these systems, which can be, of course, quite expensive in an area that you're going to get the most return from. So again, really understanding the thermal conductivity, the thermal properties of those surrounding areas is going to be really important. All right, so a few examples there on the MTPS, but again, this presentation here today will kind of cover all three methods. Next, we'll take a look at the Flex Transient Plane Source, or TPS. So the TPS, few noteworthy things to highlight, is a double-sided sensor. So right there, you'll see some differences between the MTPS, which is single-sided, compared to the TPS. The TPS does provide conductivity, as I mentioned, but also measures thermal diffusivity. It offers the greatest flexibility over experimental parameters. So what we mean by this is really the timing and power. These are two parameters that need to be set for any type of measurement. But with the TPS, you as a user have full control over this. So puts a little bit more onus on you as the user to set these up accordingly, but you do have full control over your test settings. One of the things to highlight is that there's no contact agent required for the TPS. This is something that I didn't really touch on in the previous slides there, but for the MTPS, some materials may require the use of a contact agent. And of course, depending on the geological sample in question, that may not be a technical fit in some cases. So the TPS, a really nice complementary aspect here. So no contact agent is needed. That sensor can go in direct contact with the material. This may not be as applicable for the geological space, but there are different utilities that are available within the TPS, things like slab, testing anisotropy, and thin films. These are things that the TPS lends itself quite well towards. If you did have specific questions or inquiries about those different functionalities of the sensor, happy to address those. Won't really be going into as much detail on those here today. The TPS, kind of as a final note, it does conform to the ISO standard 22007-2. So again, sometimes a specific standard is of interest to some groups. That is what the TPS conforms to there. So again, we'll take a little look at the principles of operation here for the TPS, keeping it quite high level here today, but effectively the sensor is placed between two samples. So again, it's a double-sided sensor. So one sample goes on top and one sample goes on the bottom side. As I mentioned, the time and power parameters, you have full control over those in the software. So you'll set those up based on the settings. And then also just to note, the TPS does come in a variety of sensor sizes. So depending on the size of sample that you're working with, perhaps certain samples will inherently require a certain sensor size to collect the data properly, but you do have some flexibility there as well. Now, at the end of the day, once you get everything set up and running, you collect your data. Really, at the end of the day, what we're collecting is fundamentally similar there between these transient methods, which is that change in temperature that occurs as a function of time. How that data is processed and analyzed, of course, is a little different depending on the methods, but that transient measurement of that heat change over time is really what's being used to determine these thermal properties. Now with the TPS, it is not factory calibrated. The settings are a little bit not the same as what I described with the MTPS. And because of that, post-measurement, there is a verification process that you essentially have to run through. There are a series of checks that you need to ensure are validated. You may need to go in and do some data adjustments. So within the data that you've collected, you may need to adjust the region that you're analyzing to a specific condition within a certain boundary. And again, essentially, there's just a little bit more onus on you as the user to go through and validate your results. So again, it can take, I would say, a little bit more time to kind of run through this process. But again, it is a very powerful tool and ultimately conforming to that ISO standard. So where the TPS really shines, as I kind of alluded to it earlier, is if you're dealing with specifically porous materials, those that may be hygroscopic in nature, some things like sandstone, pumice, these could be incompatible with some common contact agents. So again, typically required for MTPS. So to test these materials, we had to have another way. I might have been thinking about the TLS sensor. There are some cases where the TLS can be inserted down into the material if you're able to, if it's unconsolidated or if it's a soft sample that you can drill into. But again, many of these samples may be too rigid or hard for that. So this is where the TPS really comes in and shines. The sensor itself can really enable testing of these materials. The sensor is designed to get good contact, even if you do have more of a rough surface. And again, the main point that I want to get across here is no contact agent is needed. And for kind of a little highlight here, I have a porous geological sample analog, concrete. There's some similarities here between different geological sample types and certain building materials that we've tested in the past. One being, of course, concrete here. This is something that has some similar characteristics. It's hygroscopic, somewhat porous, and it's a material that lends itself quite well to be tested via TPS. The results that I'm going to show here, this was all done at ambient conditions, about 23 degrees Celsius. The sensor is actually moved to 10 different places around the sensor or around the sample's diameter. And kind of essentially here, we're looking to kind of get an understanding of variation that may be present throughout the material, because it is not, I would say, a truly homogeneous sample. There's, if you're to look at the inside of those cement blocks, there's some, of course, local heterogeneity that is present. But what we can kind of see from our test results is, there was a little bit of a swing, plus minus 5% on either end, but coming in with an average thermal conductivity of about 0.52 watts per meter Kelvin. And again, this is something that, if the material itself was able to accept the contact agent, the MTPS would be a great option here. But for this sample in particular that we tested in-house, the contact agent was just simply absorbed readily into the material. So again, the TPS really shining as the best option here for this type of sample. And of course, this lends itself well to a range of other sample types. Again, really anything that is porous in nature, generally the TPS would be the recommended option. But of course, the effective thermal conductivity really depends on the moisture, the composition, and porosity. some different values taken from literature here. You can see that for a singular type of material, there's, again, quite a wide range. And this is partially related to the fact that these naturally occurring samples are not as controlled as what you would get in a sample produced in a lab. So these inherent variations that are present can be important to understand, and really classifying them across a range to seeing where they fall within the scope of that material type. All right, and then lastly here, we do have a little bit of information on the transient line source, or TLS. So the TLS, it's a needle probe style sensor. It is the one that I would say is most different in design compared to the other options on Trident. TPS and MTPS both being flat sensor surfaces that come in contact with the sample. The TLS, of course, is this needle probe. And the TLS, it does conform to two ASTM standards, ASTM D5334 and D5970. And the prior there, so D5334, this is specific to testing a range of geological samples, so aggregates, soft rocks, soils. This is really a method that is directly related to that within the standard itself. Now, the TLS is completely encased in stainless steel, so it does make it, quite robust to damage from materials. So a lot of the times we have groups working with more chemically aggressive substances, sticky, tacky, or abrasive materials. Again, the TLS is a really good option there for testing these types of samples from a sensor robustness standpoint. The TLS will carry some similarities to the TPS in that there is some requirements on you as the user to set up your test parameters manually. So you will need to adjust those. There's a probe calibration that needs to be done with the TLS. This is the one sensor that you will have to go and calibrate the probe with a standard material. And then also there's a data analysis portion that you have to go in through, do some adjustments and things like this as well. So it does carry a little bit more user requirement, again, compared to the MTPS method. But again, we'll kind of just do the high level principles of operation here. The TLS, again, similar to the previous two in that the sensor is delivering this heat pulse. In this case, it's radiating out from the body of the probe itself. And this will enter into your test material. So as you can kind of see in the image there, you have an idea that we're evaluating a much larger volume of sample compared to, let's say, the MTPS and TPS. And because of that, the needle probe does need to be fully immersed in your test sample. So inherently, there's generally a larger volume requirement for this method to be able to fully submerge the sensor itself. But again, end of the day, once you set things up, you start running, collecting your data, you'll see something like you've seen similar, that delta T as a function of time, which is collected within the software. And again, there's a little bit of a manual data adjustment process that you have to run through to kind of go through and validate those results. So for the kind of the example data, we're looking at some testing of soil. This would follow, again, kind of a similar process as outlined in the ASTM D5334 standard. But, of course, it's still wintertime up here in Canada as well. It's, the snow on the ground, can't really access that topsoil quite as easily. So for an analog here in the highlight, we're doing testing of some potting soil. So, kind of the bag of soil you can go and get from these, Home Hardware, Home Depot supply stores. And specifically here, we're looking at a few different aspects, the influence of packing and then also saturation. So taking a look at how really the densification and saturation influence these results. Now, I do just want to make a note that topsoil is made up of quite a different material than potting soil. Typically speaking, you have your sands and clays with various organic compounds, different materials in there. Whereas potting soil, it's generally viewed as much lighter and almost fluffier in a sense. It contains things like peat moss, perlite, and other organic materials as well. But because of that, inherently the topsoil's heavier, denser properties, you will generally expect to see some differences if you're just testing them in kind of similar scenarios. But again, for kind of an example here today, hopefully to illustrate the point, the TLS was used for these different types of potting soils. So the goal here was to assess the packing or densification differences that could occur between, let's say, a loose sample and something that was packed down to a significant degree. And then also looking at the influence of saturation. So whether that's partially saturated or fully saturating a material, kind of seeing how that thermal conductivity plays a role. And then ultimately just taking a look at how these potting soil results compared to a typical topsoil value. So there's a lot of literature results out there on topsoil in different regions, but just kind of roughly seeing how they compare to each other. So before we get into that, I do just want to make a highlight. Most of the previous examples we looked at, whether it was with the exception of the fluid, these solid samples, I want to highlight, will behave quite differently than an unconsolidated sample. So you can imagine these aggregates, powdered samples, things like this. A lot of the time when you're studying an unconsolidated sample, like a soil, the effective thermal conductivity is often highlighted. What we really mean by that is that the influence of the sample's density, so how much it's packed down, will have a net influence on the results. So a less dense sample, if you kind of look at the boxes, you see those three different boxes. The one that is less densely packed will have more air voids present in the evaluated volume. Air is, of course, a very good insulator, so your net material that we'd be looking at would be more insulative in nature and therefore have a lower thermal conductivity. Now, the exact relationship between the density and the effective conductivity depends on a variety of factors. So, the size of the material, the particles that are inside, how they pack together, what they're made out of course. There's a lot of things to consider there, but generally speaking, lower density will be lower thermal conductivity. Now, just kind of from the summary and results here, first taking a look at the loose compared to the packed sample. So again, basically the needle probe was first just inserted into the containment vessel that had the soil, took some measurements, and then we also looked at a packed sample. So basically taking that same vessel, packing it down, but again, in all cases, making sure the probe was fully submerged. And we can see that kind of as we would expect, the packed sample did come in at a higher thermal conductivity, approximately 35% higher in this example. And again, this is just somewhat analogous to the kind of pointing out that the densification does play a specific significant role there. We then kind of took the packed sample, removed it, saturated it with a small amount of water. This is very minimal, actually. I believe it's probably close to maybe 5% by weight here, just to kind of partially saturate the sample. And then again, packed it all down and then inserted the probe in, took some measurements. And then we saw again a further increase by about approximately 22% here. And again, this makes sense as to what you may expect. What we're seeing here is that the TLS being inserted previously into that kind of, let's say, the dry condition, any of that kind of those little air voids may be filled with just the air and the material. Whereas if you're saturating it, perhaps you're getting some of those water molecules filling in that space, improving that heat transfer by effectively removing some of the evaluated air in that region. There's, of course, perhaps changes to the structural component of the organic materials that are in there as well, but this can have quite a synergistic effect as you kind of modify these different conditions. And then kind of just looking at some typical topsoil values, they've been shown to range, kind of one publication noted, ranging anywhere from about 0.15 to 0.8 watts per meter Kelvin. Again, a lot of things to consider there, the packing, the density, composition, things like this. But what we're showing that is, in our loose and our packed state, even in the saturated state, we're coming in pretty much at the very bottom end there or below what is expected of most topsoils. And again, related to the fact that this potting soil is it's a different material. It's, again, lighter, not as dense. This makes sense that you would experience a lower effective thermal conductivity compared to that of something more densely packed like topsoil. But again, a nice little analogy here on kind of just looking at the different sample formats and which methods may be more appropriate. All right, so that kind of comes to getting close to the end of our session, but just a few concluding remarks here. one of the big takeaways, of course, is that thermal conductivity is an important material property for geological samples across various applications. So again, whether it's geothermal energy, extraction, what have you, thermal conductivity is one of the most important properties of interest, along with other factors such as heat capacity, thermal diffusivity, and others. But due to the wide variety, the different types of samples and kind of formats that they may be present in, really having a multi-method approach is generally recommended. Now, whether that's a transient technique, steady state, what have you, the highlight or the thing that I was hoping to get across is that, of course, these transient methods do offer some very unique flexibility with respect to the conditions and the setups that you can use. But again, even within the three methods that we offer, some samples are better suited for testing on one method than others. And, it's really having that toolbox approach that gives you the best chance of getting the most accurate and representative test data. So C-Therm's Trident is configured with these three methods that we've talked about today. So MTPS, TPS, and TLS does provide a fairly robust solution for a wide range of samples and test conditions. So I would just like to say thank you for all of those in attendance here today. Again, my name is Ari Heikkinen, application scientist at C-Therm Technologies. My email is on the screen there. Also, I've had good conversations with folks after the fact. Message me on LinkedIn. If you do have any questions or really want to go into some of these topics in further detail, definitely feel free to reach out. I know there are some questions that have been posted in the chat box that we'll get to here at the end of the session, but if you wanted to go maybe further than that, always happy to reach out if you did have those more in-depth questions to discuss. Also, just to highlight, we do have a range of resources available on our website, www.ctherm.com, whether those are past webinars on various topics, a tech library, so these include everything from publications to application notes that we've developed. These are free resources that you can take advantage of, so please feel free to check those out. I will just make a note, some upcoming events. So we do have one coming up here later in March in Amsterdam, the Silicon Expo Europe. We will be present there, having some folks from our team. So if maybe you have some colleagues in this type of application space, or if you yourself are in that area, we'll be there and presenting. So definitely feel free to stop by. If in person isn't doable, we do have some upcoming webinars. One of them that we'll just wanted to plug here is coming up on March 9th. It's really a focus on DMA, which is thermal mechanical property. It's outside of our kind of traditional thermal conductivity webinars, but we do have a guest speaker, Jonathan Martins from ARDL, coming to talk about some of how he's using DMA for some of the work that they're doing. So if you, again, or if you have some colleagues that are interested, please feel free to sign up for that. And then, lastly, give us a follow on LinkedIn. And if you are looking to stay up to date with, new webinars, different blog pieces, content development, this is basically the best place to find it. This is where we'll post all of our new information. So if you do want to keep in touch, definitely do so there. And then, if there's next steps, if you really wanted to kind of really take a further in-depth look, you wanted a quote on one of these instruments or booking a demo, discovery call, feel free to do so. All of our information is available on our website and through some of the various links that Angan has posted in the chat box here today. So that said, it's coming to our Q&A session. So at this point, I'm going to go ahead and stop the recording. For those of you that are signing off, it was a pleasure. Hope you got some good information. For those of you that are interested, please stay on the line and we will continue.